Alright, so again, this is section 1.4, and we're looking at one-sided limits. And the reason we want to talk about that sort of thing are things like closed intervals. So a one-sided limit we designate either from the right or from the left. So from right, what we do is we would say something like the limit as x goes to c, and we put a little plus up here of f of x. And so what's happening here is there's c, and we are coming in this direction. We're looking at the path coming down this way, and we're wondering, you know, what happens as we come into this point, and does that exist? So we would only put in values that were greater than c to check our limit. And then from the left, same basic notation, the limit as x goes to c, but we put a minus there, f of x. And so in this case, there's c. You know, we're looking at this path because we're coming in from the left over here and asking, do we have a nice limit? Does it head to something? And so, you know, for instance, if we take f of x equals the square root of x, then, you know, again, that's a really nice function for x greater than or equal to 0. And so we would have that x, as x goes to c from the right of the square root of x, that equals 0. But if we come in from the left, the limit as x goes to c from the right, square root of x is undefined. Okay, so you know, it's pretty much that simple. I could look at a graph, something like that, and you know, we get you know, again, it's usually reasonably obvious if I'm looking at a graph. It can definitely be a little more difficult algebraically. But you know, that's what we have there. Now we have a theorem, you know, that says, hey, you know, if the limit as x goes to c from the right of f of x is equal to the limit as x goes to c from the left of f of x, then the limit as x goes to c of f of x exists. Now, this could have been written out much like continuity, right? Because in this first statement up here, I'm really saying three things. I'm saying the limit here exists, I'm saying the limit there exists, and then I'm saying they're equal. So I'm really saying those three things just like in continuity, and then the limit in general exists. And so on a closed interval, so continuity on AB, so if I write it that way, it's a closed interval. What I need is continuity of, no, on AB of f of x. what I need is that the limit as x goes to c of f of x exists, and f of c equals that limit as x goes to c of f of x for a strictly less than c strictly less than b. So that would be on the open interval ab. So we have continuity. So this is continuity in here, right? Again, f of c exists, the limit exists. I said that over here, and but I really said it again there that the function exists, the limit exists, and they're equal. So it's continuous in the open interval here, and then at the endpoints, as x goes to a from the right, that limit of f of x equals f at a, and the limit as x goes to b from the left, because that's the right-hand endpoint, of f of x is equal to f at b. So that would be continuous on a closed interval. It's continuous on the inside, and again, from sort of a picture standpoint, as we head to the edges of our interval, everything matches up nicely. All right, so we would expect here's A, here's B. You'd expect nice dots, something like that for continuous. So continuous. And if it wasn't continuous at the endpoints, say, we might expect either something like that, because you see it's just not defined, or I could put it down here, and this is discontinuous. Okay, so that's this idea of left-handed, right-handed limits, and why we might care about it, because we're looking at, say, closed intervals, and we want to look at those ideas. Okay, I think that's good for this video.